Section 3 is apparent forces in circular motion. So right off the bat, we have this idea of centrifugal force. So like the gravity, the scrambler at the carnival, centrifuge, we have this word centrifugal force. You've probably heard it before. So a force that seems to push an object to the outside of a circle, you might hear this word centrifugal force. Does this force actually exist? The answer is a very large, emphatic 3 exclamation point. No, this force does not exist. What's really going on here is you have a centripetal acceleration that is pulling the body towards the center of the circle as it tries to move in a straight line, but we have this acceleration that is pulling it toward the center of the circle. So what happens is it bends around in a circle, right? But chances are it's in some sort of container. So like the scrambler at the carnival or the gravitron at the carnival or your vehicle as you're going around a curve, you feel your body being pushed into the door of your car or the edge of the carnival ride or whatever. So it feels like there's this force that's pushing you up against the edge of the object. And that's where this idea of the centrifugal force comes from. But that force actually doesn't exist. What you're feeling is this acceleration towards the center of the circle. And that acceleration towards the center of the circle is what's creating this centripetal, not centrifugal. It's actually towards the center of the circle that the force is actually headed, not towards the outside of the circle. So, very important point that needed to be made. Make sure that you understand this one is not there. Okay, it is centripetal, not centrifugal. Okay, so apparent weight and circular motion. Now that we've cleared that up, hopefully. So imagine swinging the bucket of water over your head. If you do it fast enough, the water stays in. So somebody else is going to say, "Oh, well, the centrifugal force." No, that's not it. It's centripetal, not centripetal. Centrifugal. So anyway, if you do it too slowly, the water is going to spill out on your head, right? If you do it fast enough, the water stays in. The roller coaster going through the loop. Okay, so that's what we have in the picture. How does the train stay on the track when the train's upside down? Aside from the fact that it has wheels on the underside of the track and so on. So, like, how does the stuff stay in everybody's pockets as the train goes over the loop? Stuff like that, right? So, the answer is the motion as we go through the loop here. We have this force that's keeping us kind of glued to the track, just like water in the bucket. As long as we're going fast enough, everything will stay put as we go around the circle. If we slow down too much, then stuff starts to fall out, like of our pockets, or if the person isn't wearing the seatbelt, then the person falls out of the train, and stuff like that. So, how does the train stay on the track? Well, in figure A, we might be at the bottom. In figure B, we're at the top. Okay, so at the bottom, we have the sum of the forces in the x direction. In this case, the weight would be down, so it doesn't show it there, but the weight is down, and the normal force is up. Okay, so we kind of see that here. And at the top, then the weight would be down still, of course, but because the track is above, then the normal force, which is the force of the track on the object, the normal force would also be down. So if we go over to figure B, we have the weight down, as we said, the normal force is up, of course. So then because the acceleration is always to the center of the circle, then the F net has to be up. Okay, so that means the normal vector is longer than the weight vector because we have an F net up. Okay, now at the top of the circle, the weight vector is, of course, down because it's always to the center of the earth. The normal force, though, because the track, again, is up here relative to the car, and that's the contact force, the normal force has to be pointed up relative to the track, but down relative to us observing this situation. Okay, so everything is pointed down, which means the F net, of course, is pointed down, but we knew that already anyway because the center of the circle is down. Okay, so everything's pointed down. Remember, the x-axis always points toward the center of the circle. So here's the free body diagram for both situations. So now at the bottom of the circle, we have the normal force minus the weight equals mv squared over r. Okay, so now if we want to talk about the apparent weight, remember the apparent weight is how you feel at the bottom of the roller coaster. If you've ever ridden a roller coaster, you know at the bottom of the hill or at the bottom of the loop, or if you're just driving in a car, you could get the bottom of the hill, you feel a little bit heavier. So we should have our normal weight and then plus some additional force, some additional weight, right? So that's why our weight apparent is going to be adding a little bit more weight than normal. At the top of the hill or at the top of the loop, we're going to have our normal and we're going to have some weight, and our weight apparent is going to be the added stuff minus our weight. So why? That's because when we are upside down, everything is going to be sort of reversed. So we have this acceleration times the mass, and then we have our weight vector sitting here. So as we go over the loop, everything's upside down. We should feel pressed into our seat as we go over the loop because of the additional force down as we're going through the loop. But just because we're upside down doesn't mean the force down doesn't disappear relative to the track. So that's why this ends up being a little bit reversed looking. So the question is, as we slow down, this guy right here, this term, if we slow down, starts to get less and less. So let me scroll up here. In the roller coaster, if V is sufficiently large, then at the top of the loop, the apparent weight can exceed the true weight, just like at the bottom. As I was saying, you're going to feel heavier even as you go over the top of the loop. And that's great. That's what we want. That's how the stuff stays in your pockets. That's how the person stays in their seat. That's how the water stays in the bucket. Okay. But as V gets slower, there comes a point where mv squared equals w. And now that becomes a problem because when mv squared equals w here, what happens? We have the apparent weight equals 0. And now the person or the water or whatever begins to feel like they don't weigh anything. They're just sitting there floating or free falling almost, right? So the normal force becomes 0. At that point, the seat is not pushing against the passenger at all. Instead, she's able to complete the loop just barely because her weight force alone provides enough centripetal acceleration. So we're relying solely on basically something called momentum, which we haven't really talked about yet. So the speed at which the normal force is equal to 0 is called the critical speed, VC, because for n to be 0, we must have the mass times the critical velocity squared over r equals the weight. So then remember W is mg. So then we have this equation simplifying down in the end to Vc equals just the square root of gr. The square root of gravity times the radius of the circle. So when the speed is less than the critical speed, what's going to happen? Well, bad things. Basically, the water falls out of the bucket, the stuff falls out of your pocket when you're upside down, the person falls out of their seat if they're not buckled in, whatever. Bad things, okay? So we have to stay faster than the critical speed on the amusement park ride that goes upside down. Otherwise, people are going to get hurt. So, motorcyclist in the globe of death, as you can see here, rides in a 2.2 meter radius vertical loop. To keep control of the bike, the rider wants the normal force on his tires at the top of the loop to equal or exceed his and the bike's combined weight. What is the minimum speed at which the rider can take the loop? So minimum speed, basically we're talking about critical speed. We're given 2.2 meter radius, and basically we just have to find V sub c. So if I draw a picture of this scenario in sort of a simple way, we have the globe of death here, and at the top of the loop is what we're talking about. So the rider is up here at the top, and sort of a free body diagram, but not really. Remember that the x-axis is always pointed toward the center of the circle, which I'm going to say is right there. And we, at this moment, have the weight down as well as the normal force down, okay? And of course, we have F net pointed down. Okay, so here we are. Everything is in the x direction. So the sum of the forces in the x direction will be the weight vector plus the normal. And that is going to equal, since we have an acceleration in the x direction, mv squared over r. Okay, so, and it's weight plus normal because both of those are pointed in the positive x direction. So the weight and the normal are basically the same thing, right? Well, not basically, they are the same thing. So I could actually say weight plus weight here. Normal is the same as weight. So this actually is 2w equals mv squared over r. And w is really mg. So really what we have here is 2mg equals mv squared over r. Oh, that's not an r. Okay. So now, basically, I'm going to solve for v because I'm trying to find v. Okay, let me draw that r in there. Okay, here we go. So I'm going to solve for v. Now, if we can see that the mass here is going to divide out. So the mass is gone, and I'm going to multiply both sides by r and square root both sides. So I wind up with v equals 2gr, and I square rooted both sides. Now, this is really the critical velocity because we're looking for the minimum speed. So I can say vc. That is a c. Okay, so we can plug in all that stuff, and we have the square root of 2 times 9.8 meters per second squared times the radius they gave us, 2.2 meters. Okay, and we plug all that stuff into our calculator. And significant figures is we have 2, so this will be 6.6. And it's a velocity. We should wind up with meters per second. And that's it. We should be going 6.6 meters per second. If we double that and add a little using our general rule, that would be like 13, probably 15 meters per second or so. Or, sorry, 15 miles per hour or so. And in that tiny little globe, that's pretty quick. So there you go. Moving on. Centrifuges are basically a gravity increaser tool. Hopefully you've seen those, or at least seen videos of them, maybe on TV or something. CSI. Take a test tube, put it in this device, and it spins it around super, super fast. Basically what they do is they increase gravity a ton so that some fluid or something like blood, because we increase gravity a ton, we're increasing the speed with which the particles in the fluid would settle out. So it separates out the blood or whatever the fluid is, so that all the heavy stuff goes to the bottom, the midweight stuff is in sort of the middle, and the lightweight stuff is at the top. That's kind of a simple idea of how that works. An 18 centimeter diameter ultra centrifuge, which means it spins really, really, really fast, produces an extraordinarily large centripetal acceleration of 250,000 Gs. G is the free fall acceleration due to gravity, remember. So that's ridiculous acceleration. What is the frequency in RPM? So first question, we want the frequency in RPM and the apparent weight of a sample with a mass of that. Okay, so 2 questions we got to answer here. First thing we got to do is figure out the frequency. Okay, actually the first thing we're going to do here is convert because we have a couple of things to do. So 18 centimeter diameter, I want to turn that into meters, and also I want to use a radius. So 18 centimeters would be 0.18 meter diameter. So the radius then would be half of that, 0.09 meter radius. And then 250,000 G, I want to know what that acceleration is in meters per second squared. So it's going to be 250,000 times 9.8 meters per second squared. Okay, so we type that into our calculator, and our calculator just gives us scientific notation on that. It says, let's see, 2.45 times 10 to the 6. Actually, it says E6. Remember that it means times 10 to the 6th power. Now, the calculator has more numbers than just that, so you have to remember to use the calculator's answer, meters per second squared. Okay, so now we know the acceleration, and we are looking for the frequency. So we want to use a formula that involves frequency, radius, and acceleration. We have a formula that does that. We have acceleration equals 2 pi frequency, this is all squared, times the radius. All right, we know all of those things except for frequency, which is what we're looking for, so this is great. I can divide both sides by the radius. This will give me acceleration over radius. I can square root both sides. This gives me the square root of acceleration over radius. And then I'm left with the 2 pi on the frequency. So I'll divide both sides by 2 pi, and that gives me 1 over 2 pi equals frequency. Okay, so now I can plug all this stuff in. I have 1 over 2 pi, square root. My acceleration is 2.45 times 10 to the 6th. Again, remember to use the calculator's answer on this. Divided by, and the radius we calculated to be 0.09 meters. All right, and we get an answer on our calculator that needs to be significant figure. We have 2 there and really 2 there. So we're going to use 2 significant figures here for our frequency. Once you get your calculator's answer and do 2 figures, we're going to have 830. Now, the units on this, we have meters divided by meters, so that's gone. We have per second squared. Square root of that is just per second. So this is something per second. Now remember, we're talking about a frequency, and that is how many times per second something happens. Well, we're revolving, so this is revolutions per second. Okay, but they wanted the frequency in revolutions per minute. So we're going to have to convert this to per minute. So if I have revolutions per second, I got to get rid of seconds, and I will do that by putting seconds on top and put minutes on the bottom. So there are 60 seconds in 1 minute, which basically means 1 revolution per second there. I'm going to have to multiply by 60. So I take my calculator's answer and I multiply it by 60. And then I significant figure this again, and I'm going to wind up with 50,000 RPM, 50,000 revolutions per minute. So if you think about it, actually, though, 830 revolutions per second, it's going around 830 times in 1 second. That's crazy. That's a lot. So it's pretty amazing what these things do. All right, so that's the first question. Now, the second question, what is the apparent weight of a sample with a mass of 0.0030 kilograms? Well, weight apparent is what we're looking for. And that's really just the net force, okay? And that's just going to be mass times acceleration. So we have the mass, 0.0030 kilograms, times the acceleration. And we'll use the calculator's answer for this, remember. So that is 2.45 times 10 to the 6th meters per second squared. But the calculator's answer again. And once we're done, then we'll significant figure this. And we get, and I'm going to use 3 on this just for fun, 7,350 newtons. Okay, there you go. So the particle was 0.0030 kilograms, and it winds up being 7,000, basically 7,400 newtons apparent weight. That's pretty amazing. Okay, so basically done here. We just have one more thing to do. The car is rolling over the top of a hill at a constant speed v. At this instant, what are we dealing with? Normal is greater than weight, normal is less than weight, normal is equal to weight, or we can't tell anything unless we know what the velocity is. So we think about this for a minute. The key to this, along with every other problem, is this is a circular path here, which means we have a center of the circle, which means the x-axis is pointing down towards the center of the circle. And because of all of these things, we have an F net because we have an acceleration, and the F net is pointed down. And because the F net is pointed down, the weight vector must be longer than the normal force. And that means the weight must be longer than the normal force. The answer must be B. Okay, that's it. That's the key. You really need to understand curvature. Gives me a center of the circle, gives me an x-axis, gives me an acceleration, gives me an F net. All of those things are true, which means you need to be thinking about those things. Just like we need to be thinking about free body diagrams, we need to be thinking about where is the center of the circle, where is the acceleration, where is the F net. That's seriously going to help you. Okay, so that's it for this section.